Hey there, this is problem set 16, where we're going to start talking about Lewis structures. Now, there are probably a handful of different ways that you could be taught how to draw Lewis structures, and some work in some conditions and some work in other conditions, and I prefer to teach some way that works in all conditions. And so what I'm going to give you here at the beginning of this video is my breakdown of how to draw Lewis structures and how to draw them the right way every time. And then as we get into the actual structures that we'll be drawing down lower, we'll just follow those rules and you can see how they apply. So I'm just going to write down the rules now and I'll refer to them later on. So rule number, or I should say rule, I should say steps. Step number one, you're going to count, I'll try and draw it a little neater, count the valence electrons. You count all the valence electrons in your molecule. 2, you're going to draw what I like to call a skeleton structure. With the least electronegative atom in the center. That is not hydrogen. So hydrogen might be the least electronegative in your atom, but since hydrogen only forms one bond, it would not make sense to put it in the center of the atom. So least electronegative, the center of the molecule. Least electronegative, as long as it's not hydrogen. All right, number 3, you're going to distribute the rest of your valence electrons. Beginning with the most electronegative atom. So since you're putting the least electronegative in the middle, the most electronegative is going to be on the outside, and so you'll start filling up your atoms with electrons, starting with the outside atoms, because they're the most electronegative. Okay, then we're going to calculate formal charge. And then lastly, we are going to minimize formal charge. By creating bonds. And that means creating like double or triple bonds where there were previously only single bonds in the skeleton structure. And I'm going to say without breaking the octet of carbon, nitrogen, oxygen, or fluorine. So if I go to the periodic table here, you might have heard about the octet rule. I think it's kind of dumb that we talk about the octet rule because the octet rule really matters for carbon, nitrogen, oxygen, and fluorine. Those are the 4 atoms that will 99.9% of the time have 8 electrons and cannot ever have more than 8 electrons in your structure. Okay, those are the ones that you're going to be dealing with that. Below this, you'll deal with atoms that can have more than 8 electrons, and behind carbon, so above carbon on the periodic table, you'll be dealing with atoms that could have fewer than 8 electrons in the final structure. And so that's why I emphasize formal charge, and as long as you don't break the octets of carbon, nitrogen, oxygen, fluorine. But we'll see that, if not in this problem set, then in the next problem set. But yeah, so those are my rules for drawing Lewis structures and getting the right answer pretty much all the time. So with that, I'm just going to go back and let's get this problem set started. All right, so A, draw the Lewis symbol for atoms of nitrogen, selenium, and chlorine. All right, what is a Lewis symbol? So a Lewis symbol is different than a Lewis structure. A Lewis symbol is just for one atom. So you essentially draw your atom, and then you say how many valence electrons it have. Nitrogen has 5. So I'm going to do 1, 2, 3, 4, 5. Okay, then selenium has 6. And then chlorine is Cl, not Ch. Chlorine has 7, so 1, 2, 3, 4, 5, 6, 7. So that would be chlorine. Draw a Lewis symbol for the most stable ions formed by lithium, magnesium, aluminum, and fluorine. Okay, so what does lithium form? Lithium forms a 1+. If you don't understand why, right, atoms are going to gain or lose electrons in order to form ions that have the same electron configuration as a noble gas. So lithium, the quickest way to get to a noble gas is to lose 1 electron, hence lithium plus. So lithium plus, so if I were to draw lithium, it would look like this. Lithium plus then would lose that electron. And often we'll draw it in brackets with a plus, or just with a plus. But, all right, magnesium forms a 2+. So then Mg by itself would look like that, but when I remove the electrons, it's going to look like that. Aluminum forms a 3+, so you can probably predict 3+. And then fluorine forms an F-, so normal fluorine is 1, 2, 3, 4, 5, 6, 7. F- has an additional electron, so that would make 8. And then I put that in brackets with the minus. So those are Lewis symbols for ions. How many valence electrons are in each of these atoms? Xenon, Sr2+, chlorine, and Cl-. So if I just pop that over there, xenon is over here. It's got its full valence shell, and so we would probably, or we would say that it has 8. Strontium 2+, strontium's right here, and so when it loses 2 electrons, we usually say it has 0. You could make the argument that it also has 8, like krypton, but typically we say if you lose it, then it's emptied its valence shell, so it has 0. Chlorine's right here. It has 7, so chlorine minus would have 8. All right, how many valence electrons do each of the following species contain? All right, so now we have molecules. So nitrogen, N2+, means I'm going to have my 2 nitrogens, and each nitrogen has 5, but then it's plus. If it's plus, since electrons are negative, when you have a positively charged ion, it is deficient in electrons. So 2 times 5 minus 1, so 9. Okay, next we've got CS+. C is 4, S is 6 minus 1, so also 9. Cn, C is 4, N is 5, so another 9. And lastly, CO, C is 4, O is 6, so that's 10. Okay, so now we are going to draw the Lewis structure for the following diatomic molecules and ions. So F2. So this is when this process is going to come in handy. So I'm gonna just gonna pull it up. Okay, so step number 1. So we're going to have F2. We're going to count the valence electrons. F2 is going to be 7 plus 7 equals 14. Draw the skeleton structure with single bonds, F and F, with the least electronegative in the middle, but this is just F's, and so I'm not going to have a center because I just have 2 atoms. Then I distribute the rest of the electrons around, starting with the most electronegative, so I have 14, so that's 2, 4, 6, 8, 10, 12, 14. So that's all my electrons. What's the next? So I'm not done yet, because for now I need to calculate formal charge. So let's talk about formal charge. So formal charge is a bookkeeping method to figure out or to describe where electrons are compared to where they are for like a pretty stable atom. So the way that we calculate this is we say fluorine usually has 7 electrons. Fluorine in its neutral state has 7. So if I look at this picture right here, I circle fluorine. How many electrons does it have, or in other words, does it own, is the words I like to use in this picture. How many electrons does it own? I would say it owns 1, 2, 3, 4, 5, 6, 7. Now it has access to that 8th one, but it doesn't own that 8th one. I care about how many it owns. So fluorine usually owns 7. In this picture it owns 7. And so because of that, because of that, you end up with a neutral fluorine. So fluorine's formal charge is 0. So if I did over here, this fluorine owns 1, 2, 3, 4, 5, 6, 7. It usually owns 7, so that means it's neutral. So I've drawn this, and now we want to minimize the formal charge by creating bonds without breaking the octet. So minimizing formal charge, that means getting the formal charges as close to 0 as you can. I'm already at 0, so that means that this structure is done. All right, NO plus. N is 5, oxygen is 6, plus is -1, so that gives me 10 valence electrons. So I'm going to have N single bonded to O. I'm going to distribute the rest of my electrons, starting with the most electronegative, so oxygen. So 2, 4, 6, 8, and then 10. Now I'm out of electrons. Now you might be thinking, wait, what about nitrogen's octet? Because right now nitrogen only has access to 4 electrons. We're not done yet, so you don't need to freak out, because we still need to assign formal charge. So formal charge on this nitrogen. Well, usually a neutral nitrogen has 5, right? And this nitrogen owns 1, 2, 3. So it's missing 2 electrons, so that's going to be 2 plus. This oxygen usually has 6. And so then here we have 1, 2, 3, 4, 5, 6, 7. So it has an extra electron, so that's a minus. Oh, come on. Okay. So next step is to minimize formal charge by creating bonds without breaking the octet of CN or F. All right, how do we do this? Well, this oxygen has a negative formal charge. It's bonded to a nitrogen with a positive formal charge. That means this oxygen has an extra electron than it normally has. This nitrogen is missing some. So in order to get those formal charges down, what I can do is I can take electrons away from the negatively charged thing. So if I erase those and make a bond with the positively charged thing. Now let's recalculate formal charge. Nitrogen usually has 5. Here it has 1, 2, 3, 4. And as a result, it's now just +1. Oxygen usually has 6. Here it has 1, 2, 3, 4, 5, 6. So now that's down to 0. So I might think this is great. I'm done because there's no more negative bonded to a positive. But this structure would still not be correct. Why not? Because carbon, nitrogen, oxygen, fluorine have to actually follow the octet rule. And right here, oxygen has access to 1, 2, 3, 4, 5, 6, 7, 8. Okay, nitrogen has access to 1, 2, 4, 6. So nitrogen's octet is not full, and it's one of the 4 atoms it has to be. And so I'm going to have to take 2 more electrons away, make a triple bond. What does this do to formal charge? Nitrogen's is 1, 2, 3, 4, 5. So nitrogen's formal charge is 0. Oxygen has 1, 2, 3, 4, 5. And it usually has 6. So it has a formal charge of +1. Okay? Because this is an ion at the end of the day, I have to box everything and put the overall charge on the outside. Now, in general, if we have to have a formal charge, if it's going to be negative, we'd rather have it on the more electronegative thing. If it's going to be positive, we'd rather have it on the less electronegative thing. In this case, though, the more electronegative thing is oxygen, and we're giving it a positive. We'd rather give it a negative and give a positive to a nitrogen. But because that octet rule has to be followed for carbon, nitrogen, oxygen, and fluorine, we're stuck with that. All right, SO, sulfur has 6, oxygen has 6. That gives me 12. Sulfur to oxygen. I'm going to fill up the most electronegative first. So 2, 4, 6, 8, 10, 12. Now assign formal charges. 1, 2, 3, 4, 5. It usually has 6, so that's +1. 1, 2, 3, 4, 5, 6, 7. Usually has 6, so it's -1. So the easy solution to this, let's take electrons away from the negative thing, make a bond with the positive thing. Now I've got 1, 2, 3, 4, 5, 6, so that formal charge is 0. 1, 2, 3, 4, 5, 6, this formal charge is 0. HI, 1 plus 7 gives me 8, so I'm going to have H bonded to I. Now I think hydrogen is probably the more electronegative thing, but hydrogen only fills up to 2 electrons, and so we can't throw the rest of our electrons onto hydrogen. It's already got access to 2. So I've got 2, 4, 6, 8. Calculate formal charge. Hydrogen usually has 1, it owns 1 right there, so 0. Iodine usually has 7, it owns 1, 2, 3, 4, 5, 6, 7, so that's 0, so I am done. And you don't need to write non-zero formal charges. There you have it. Those are some simple diatomic molecules, again, following these rules. Now, there are other rules you could follow with these simple molecules. You could just pay attention to satisfying their octets, but I believe in using one set of rules that work all the time. And as a result, that's why I'm kind of going through a little bit more complicated process for these easier molecules. All right, for each of the following molecules or ions, indicate the total number of valence electrons present. Draw the Lewis structure, indicate the number of lone pairs, bonding pairs, single bonds, double bonds, triple bonds. All right, so by drawing the picture, we're going to answer all of these questions. So, water is H2O, so that's, I'm counting the valence electrons. That gives me 10 valence electrons. So, oxygen in the middle. You want the least electronegative in the middle, which would be hydrogen, but I can't put hydrogen in the middle because it only makes one bond, so I'm stuck with oxygen. Did I do that math right? 2 times 1 plus, okay, sorry, that should be 8. Okay, so I've used 2, 4, and now I can't put them on the hydrogen, so 2, 4, 6, 8. Now you might be thinking, oh, but I drew it like this, which is probably the more natural way to draw it. Nothing wrong with that, so I'll just do it this way. Here we go. I check my formal charges. The hydrogens want 1 electron. They own 1 electron, so they're all 0. Oxygen owns 1, 2, 3, 4, 5, 6, so it's 0. That means we're done. Okay, now it asks number of lone pairs. There's 2 lone pairs, right? 1, 2, and 2. Oh, okay. The problem's kind of worded weird. It asks for lone pairs. So 2 lone pairs, and it asks for bonding electrons. There's 2 bonding pairs, but it wants bonding electrons, so I would say that there's 4 bonding electrons. Just like there are 4 there are 4 lone electrons, because it asks for lone pairs, there's 2 bonding electrons, there's 4. Single bonds, double bonds, and triple bonds, 1 single bond. Sorry, 2 single bonds. 0 double bonds, 0 triple bonds. So I'll just kind of write out the answers like that. That's simple enough. Okay, ammonia, NH3. So total valence electrons, 5 plus 3 times 1 gives me 8. Nitrogen's got to go in the middle. Hydrogen, hydrogen, hydrogen. I've got 8 electrons, 2, 4, 6, 8. Check formal charge. Hydrogens are all 0 because they own 1 electron and want to own 1 electron. Nitrogen wants to own 5. It owns 1, 2, 3, 4, 5. So they're all 0. That means we're done. And so we have 1 lone pair, 6 bonding electrons, 3 single bonds, 0 double bonds, 0 triple bonds. Okay, methane. So I've got 4 plus 4 times 1 gives me 8. C is going to go in the middle. Hydrogen, 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 hydrogen. How many? I need 8 electrons, 2, 4, 6, 8. So I've got all my electrons on the table. Formal charges. Hydrogens are all going to be 0 because they own 1 electron. Carbon wants to own 4. It owns 1, 2, 3, 4. So it's got a formal charge of 0. That means we're done. And so what do we need? We have 0 lone pairs, 8 bonding electrons, 4 single bonds, 0 double bonds, 0 triple bonds. Ammonium ion. Ammonium is NH4+. If you're curious about polyatomic ions, you can go back to chemical naming in problem set 15 where I talk about those. There are some that you just need to know the names of, and ammonium is one of them. All right, NH4+, that gives me 5 plus 4 times 1 for the hydrogens, minus 1 for the plus, gives me a total of 8. Nitrogen's got to go in the middle because hydrogen can't. Eight electrons, 2, 4, 6, 8, they're all down. Let's calculate my formal charge. 0, 0, 0, 0. Nitrogen wants to own 5. It owns 1, 2, 3, 4, which means it's deficient 1, which is going to give a positive. Okay, so we're left with a formal charge positive. Well, that makes sense because our overall charge needs to be positive because it's NH4+. So we have 0 lone pairs, we have 8 bonding electrons, 4 single bonds, 0 double bonds, 0 triple bonds. We're just flying, aren't we? All right, nitrogen trichloride, NCl3. All right, so I'm going to count them up. 5 plus 7 times 3 gives me 26. I'll put the least electronegative in the middle. And look here, chlorine is actually less electronegative than, nitrogen is less electronegative than chlorine, I believe. Why don't I just pull up electronegativity chart? Awesome, so, sorry about that. We have this electronegativity chart. Nitrogen is 3.04, chlorine is 3.16, so nitrogen is less. In addition to the electronegativity rule of putting the lower one in the middle, you also just kind of gain an intuition. I've got 1 nitrogen and 3 chlorines. Chances are the nitrogen's in the middle of the chlorines. So, okay, got my skeleton structure, and I've got to distribute all my electrons, all 26. So I've used, and I'm going to start with the most electronegative, which is chlorine. So 26. So I've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, sometimes people will freak out at this point and say, I don't know what to do with the last 2. Well, you just put them on the next atom, nitrogen. Okay, so I've got my 26. Now I got to calculate formal charge. Chlorines want to own 7. This chlorine owns 1, 2, 3, 4, 5, 6, 7. So the result, it's 0. All of these are in the same condition, so it's 0. Nitrogen wants to own 5. It owns 1, 2, 3, 4, 5, so it's 0. Awesome, I'm done. And again, you do need to write non-zero formal charges. You don't need to write 0 formal charges. All right, so we have how many total lone pairs? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 6 bonding electrons, 3 single bonds, no double bonds, no triple bonds. Chlorite. What is chlorite? Chlorite is ClO2 minus, I believe. Yep. Okay. So let's start. We've got 7 plus 6 times 2, and then we have a minus charge, so plus 1 gives us a total of 20 valence electrons. Chlorine is the least electronegative, so we're going to have chlorine with my 2 oxygens. 20 electrons. I've used 2, 4, 6, 8, 10, 12, 14, 16. And then 18, 20. There we go. Okay, next step is to calculate formal charge. Oxygen wants to own 6. Here it owns 7, so it's a minus. This oxygen wants to own 6. Owns 7, so that's a minus. Chlorine wants to own 7. It owns 1, 2, 3, 4, 5, 6, so that's a plus 1. Okay, so now the last step that we haven't had to do because our formal charge has been good so far is we want to minimize formal charge by creating bonds. So I have a negative thing bonded to a positive thing, so I can take electrons from the negative, make a double bond with the positive. Now this formal charge is 0, and this formal charge is 0. Okay, so then I would put this in brackets with a negative charge. But we're actually not done with this molecule, okay, because I could have just as easily made that double bond on this oxygen. And so when that's the case, we have what we call resonance, and more specifically we have 2 structures that are equivalent resonance forms. So you could have equivalent resonance forms and inequivalent resonance forms. These are equivalent because there's nothing telling you to put the double bond there instead of there. So what we do is to represent the fact that it could go in either place, we draw both structures with a double-sided arrow between them. And this now has a formal charge negative there. Overall, there we go, overall negative. So that would be everything you need to draw for a chlorite ion. All right, sulfur difluoride, sulfur di-SF2. It's going to be 6 plus 7 times 2 gives me 14, so 20. Sulfur in the middle with my 2 fluorines. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Formal charges 0, 0, 0. And so that leaves me with this. Oh, I haven't. Okay, I'll jump over. This one has 1, 2, 3, 4, 5, 6, 7, 8 lone pairs, 4 bonding electrons, 2 single bonds, 0 double bonds, 0 triple bonds. Let's go up and do this one up here. This has 1, 2, 3, 4, 5, 6, 7 lone pairs, 6 bonding electrons, 1 single bond, 1 double bond, and 0 triple bonds. All right, acetate. Acetate is CH3COO minus. Okay, this is a little bit more difficult to draw. The reason is it has 2 central atoms. So, but the way that it's written kind of gives you clues on how to draw it. So they write CH3. So CH3s look like this. CH3s are going to be on the end of a group because carbon needs to make 4 bonds. So it's going to have 3, and then the next one is going to be to this next atom, this carbon, right? And then I have 2 oxygens. And the way that's going to work is I'm going to have 1 oxygen like that, 1 oxygen like that. Okay. What I neglected to do was add up all of my electrons. So here I'll have 4 plus 3 plus 4 plus 2 times 6 plus the extra 1 gives me a total of 24, I think. So I've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 22, 24, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. There we go. Do my formal charges. Here I get all the hydrogens are 0. This carbon is 0. This carbon wants to own 4. It owns 3, so it's plus 1. This one's be negative. This one's negative. So what can I do? I can make myself a double bond. Bam. That's now 0. And I got my negative, which is what I should have because of the chloride ion. But here I can draw a resonance structure because I could have put the double bond on the other oxygen. So there's my resonance form. So then we would say, okay, how many lone pairs? 1, 2, 3, 4, 5. Bonding electrons, 2, 4, 6, 8, 10, 12, 14. We have 1, 2, 3, 4, 5 single bonds, 1 double bond, 0 triple bonds. Hydrogen cyanide. Hydrogen cyanide is the cyanide ion, the hydrogen on it, HCN. So 1 plus 4 plus 5 gives me 10. Least electronegative in the middle is going to be carbon, with my nitrogen and a hydrogen. 2, 4, 6, 8, 10 valence electrons. Now I formal charge. This is 0. 1, 2 means it's a plus 2 because it wants to own 4. This wants to own 5. It owns 1, 2, 3, 4, 5, 6, 7, minus 2. So I can make a double bond there, and now this is minus 1, and this is plus 1. And so I can just do it again, make a triple bond. And I just have to make sure carbon and nitrogen have octets satisfied, which they do. That's going to give me 1 bonding pair, 1 lone pair, 8 bonding electrons, 1 single bond, 0 double bonds, 1 triple bond. Carbon monoxide, 4 plus 6 gives me 10, CO, it's my skeleton structure, 2, 4, 6, 8, 10. Formal charges give me 1, 2, 3. It wants to own 4, so that's going to give me a plus. 7 wants to own 6, that's a minus, so I'm going to get rid of those by making a bond. Now my formal charges are 0, but my molecule is not done. The reason is I want my formal charges to be 0 without breaking the octet of C, N, O, and F. And in this picture, as you can see, oxygen has access to 8 electrons, but carbon only has access to 6. And the only way I can solve that is to make a triple bond between carbon and oxygen. That's going to leave me with a negative formal charge there and a positive there. But we just have to deal with that because we can't break the octets of carbon, nitrogen, oxygen, and fluorine. So that leaves us with 2 lone pairs, 6 bonding electrons, 0 single bonds, 0 double bonds, 1 triple bond. All right, so these were relatively simple Lewis structures compared to what you'll see on problem set 17, but the rules will be exactly the same here as they will be on problem set 17. All right. How many bonding electrons in 630 milligrams of phosphorus pentafluoride? Well, first thing here is to draw phosphorus pentafluoride. It has 5 plus 7 times 5 is 35, so 40 total electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Okay, and if you, it's an F. If you were to calculate formal charges, you'll see that there's 0 for everything, so my structure is done. So I know that, I'm looking for how many bonding electrons in 630 milligrams. Well, I know that one PF5 molecule has 10 bonding electrons, based on this picture, 2, 4, 6, 8, 10. So if I can find how many PF5 molecules there are in 630 milligrams, then I can just multiply that by 10, and I get my total number of bonding electrons. So if I have 630 milligrams of, move it down, 630 milligrams of PF5, if I want to get that to molecules, I need to get it to moles. If I want to get to moles, I need to get it to grams. So I know there's 1,000 milligrams in 1 gram. Phosphorus pentafluoride has a molar mass of 125, 126 about grams of PF5 in 1 mole. And 1 mole of PF5, 6.022 times 10 to the 23rd molecules. So literally, if I were to do the math now, I'd find how many of these there are in 630 milligrams. But I don't care about that. I want one step further. I know that 1 molecule of PF5 has 10 bonding electrons. Just grab my calculator, do the math. And I get, with 2 sig figs, I get 3.0 times 10 to the 22nd bonding electrons. Okay. Chlorofluorocarbons, CFCs, are compounds linked to depletion of stratospheric ozone. They're also greenhouse gases. Draw Lewis structures for the following chlorofluorocarbons. All right, CF3, 4 plus 3 times 7 plus 7 gives me 32 electrons. Carbon in the middle. Cl, I got 3 Cls. Start filling up the most electronegative, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Formal charges are all 0. I am done. Now you notice fluorine and chlorine are both halogens, and so they bond very similarly because they both have 7 valence electrons. And so if I go from 3 chlorines and a fluorine, it looks like this. Now I can go 2 chlorines and 2 fluorines. You can see why it would just look very similar. Now some people will draw it like this, with the fluorines opposite each other and the lone pairs on there. These two molecules are exactly the same. When we talk about three-dimensional structures and shapes of molecules, you'll recognize that, but both of these are perfectly correct. Neither is better than the other. Okay, now I have 1 chlorine and 3 fluorines. All right, this Freon 113, you can see that they have this carbon bonded to a carbon. So that's kind of showing you that there are 2 central atoms there. And this one has a fluorine and 2 chlorines, and this one has a chlorine and 2 fluorines. Again, in Lewis structures, as long as each atom is connected to the correct atom, the actual arrangement of them doesn't matter. So I could have flipped this chlorine and this fluorine if I wanted. It doesn't matter in a Lewis structure. And the last one, we've got C bonded to a C with 1 chlorine and 2 fluorines. And this is 1 chlorine and 2 fluorines. I can throw my lone pairs on there. Sometimes if you Google Lewis structures, you'll see them drawn without the lone pairs. But at this point in your chemistry education, you should be drawing the lone pairs on there. All right, formic acid, HCOOH, is the smallest organic acid and was originally isolated by distilling red ants. Draw its Lewis structure given in the connectivity. So they give you this connectivity. Okay, whites are going to be hydrogens, blacks are going to be carbons, reds are going to be oxygens. So I've got a carbon, oxygen, hydrogen, and you don't have to draw them at that angles. I'm not going to. Carbon, oxygen, hydrogen, oxygen, hydrogen. Okay, but I'm not done yet because I haven't figured out formal charges and I don't have lone pairs. So let's count them up. I got 1 plus 4 plus 6 plus 6 plus 1 gives me 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, formal charge of 0. This is a formal charge of plus 1. 0 plus 1. Sorry, 0. That's minus 1, so I'm going to make myself a double bond here. Make that 0 and that 0. And all the formal charges are 0, so that's it. Labels on household cleaners. Caution against mixing bleach with ammonia because they react to produce monochloramine and hydrazine, both of which are toxic. Draw the Lewis structures for monochloramine and hydrazine. All right, so here I have 5 plus 2 plus 7 gives me 14. Nitrogen is least electronegative other than hydrogen, so I'm going to get my hydrogens coming off my chlorine. 2, 4, 6, 8, 10, 12, 14. And now I do formal charges. I get 0, 0, 0, 0. So I'm done. That's monochloramine. Hydrazine. Hydrazine with this N2 actually ends up having 2 central atoms. And then I get my hydrogens coming off. Again, whether or not you can come up with that on your own at this point, it's hard to say, but you do gain an intuition for these things over time. So this is 4, so 7 times 2 plus my 4 from hydrogen gives me 18. 2, 4, 6, 8, 10, 12. Did I do that right? Nitrogen has 5. So 14, 2, 4, 6, 8, 10, 12, 14. Formal charges are all 0. That's hydrazine. Draw the Lewis structure for phosgene, COCl2, a poisonous gas used in chemical warfare during World War I. Okay, so 4 plus 6 plus 2 times 7 gives me 24, I think. I have carbon in the middle because it's the least electronegative. I'm going to have, what do I have? An oxygen, chlorine, chlorine. Start filling up the most electronegative. So 2, 4, 6, 8, 10, 12, 14, 16, 20, oops, 22, 20, hold on. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Formal charges. The chlorines are going to be 0, carbons +1, oxygens -1. So to get rid of those, I can make a double bond. Now I've got zeros everywhere. And there's your Lewis structure. And that's it. So hopefully this problem set and this set of instructions for how to draw Lewis structures help you out. I would refer you to this video for problem set 17 when we start doing Lewis structures that are a little bit more complicated.